Okay, and now just as we did to derive this equation, we're going to impose constant returns to scale so that in the profit maximization problem, we get something very easy to work with. So after cost has been minimized, the same industry is going to maximize profits. Profits will be PIYI minus CI of W1, W2. And here we'll choose YI. And I should say, of course, here over the minimization, we're choosing the inputs. Okay, so under constant returns to scale, what does that assumption buy you? Well, remember, you can just pull this YI right out front of the cost function. And so we don't need to consider partial CI, partial YI, or in other words, that's going to be equal to 1. And so the first order condition for this problem just gives you PI equal to CI of W1, W2, P1 up to PI 1, or really the unit cost of, minimal unit cost of producing the output. Okay, and so now I won't rederive exactly how we got here with the shares just to save time, but I think you guys can see exactly how that's going to work at this point, given that we've set it up in the same way. And so what you get if you do this, if you log linearize this equation, is this the change in price in sector I will be the share spent on this kind of raw initial factor 1 times the change in its price plus, now here I'm going to define some new notation. So these shares, I'm going to kind of keep using the same notation that we used over here, just in a clear way to keep track of the industry that's using it and the factor that's referring to, which is here 1 and 2, rather than capital and labor. Now when I move to intermediate inputs, and you'll see why this is the case, I'm going to switch to this notation, big capital phi, which is going to be a matrix, keeping track of a lot of different things. But for the moment, we're just going to consider elements in the ith row of this matrix and the jth column. And that entry is going to be the share that industry I spends on intermediate input j. So does everyone see how this equation really is exactly the same as this equation? We've just added more inputs and changed a little bit of notation. Is that clear? Okay. So one thing you might notice here, and so now I want to talk a little bit about what are some of the weaknesses of this approach if we just consider one industry in isolation. So let's think about what's a good example in this room. So the manufacturer that makes this chair. So there's this stretchy fiber on this chair that's produced initially actually using oil. There's a foam cushion in this chair, which is also an oil product. But if you actually look up the industry that produces this chair, you'll see from the input-output tables, which we'll discuss a little bit more shortly, that they spend almost nothing on oil. So their actual direct purchases of oil are almost nothing. They spend a little bit on inputs from the petroleum refinery sector, but they primarily spend money on petrochemicals and other organic chemicals. So if you look at this equation, suppose somebody comes to you from the company that produces these chairs and says, I'm scared, oil prices have gone up. How much are my costs going to go up? You might just say, well, suppose input 1 here is oil, is a natural resource. You don't actually buy any oil. The share is 0, so you don't have to care about the increase in the oil price. Now, is that going to be right? Does that sound right to anyone? No. So what's going on? Why is that the case? Well, the increase in the oil price is going to increase prices in sectors that directly buy oil. And so some of these intermediate input prices are going to go up, and in particular, the price that petrochemical manufacturers charge, the price that other organic chemical manufacturers charge. and the like. So how do we see that exactly? Now you may notice that this price on the left-hand side is one of the prices that's over here. So this is back to Pedro's question. We're modeling the industries that are producing the intermediate inputs, and so that shows up as a bit of a fixed point